is by Wang from East China Normal University. She will speak about topological K-theory for discrete groups and index theory. So our formula is the following. We have 35 minutes for talk, including questions.
Oh, I see. Okay.
So if you expect
I
questions, please.
Okay, I see.
So please start.
Okay. Thank you so much for the introduction. I would like to thank the organizers to bring me to this very interesting conference. Today, I'm going to talk about my joint work with Carrillo Rouse and Wang. And this talk is about index theory in the context of non-commutative geometry. And the content of my talk will be a brief introduction on higher index theory, and followed by the main result. So the story starts from the study of elliptic operator, index theory of elliptic operator. If we look at the simplest case, that is for a closed manifold, an elliptic operator is Fredholm, which means that the dimension of the kernel and the dimension of the co-kernel are finite, and their difference is a very stable invariant, both analytically and topologically, and it's called the Fredholm index. Takes values in Z, and immediate generalization of this index is when we impose a compact group action on the manifold, and allowing and requiring the elliptic operator to be commuting with the group action, and in that case, the kernel and co-kernel of this operator would be a finite dimensional space, which is invariant under G action, and in that case, that can be the difference of these two formal difference. The formal difference of these two spaces can be regarded as an element in the representation ring of the compact group, and in that case, we call this the equivariant index of the elliptic operator. And in another direction, one can consider Dirac operator on some manifold M, but we twist that Dirac operator by some connections, namely flat U1 connections, and such connections can be modeled over a torus, the so-called Albanese torus, and associating a connection to the Dirac operator will each give you a formal difference of vector spaces, and then you let this connection change in the torus, in the space parameterized by this torus. Then this formal difference of spaces taking the family will be regarded as an element in K-theory, roughly, in the sense of topological K-theory. And all these index theory in different contexts can be unified in the setting of higher index, which considers this situation. If M is a compact Riemannian manifold acted properly and co-compactly by a group gamma, then there is a then if we consider an elliptic operator D on this manifold, which is invariant under this group action, there is a higher index inside the operator algebra K-theory of some algebra related to this group. In this lecture, I'm not going to tell you about what that is, but that is some generalization. This object is some generalization of the three examples we discussed previously. For example, if this gamma, this symmetry group, gamma is trivial, in that case, M would just be a closed manifold, and in that case, this index would just be inside Z, because when gamma is trivial, this group reduces to Z, and that is exactly the Fredholm index. And when gamma is compact group, this K group can be computed as the representation ring of this gamma, and that is exactly the equivariant index in the second example. And in the third example, it is when this gamma is z to the n, and if you consider the Pontryagin rule of that z to the n, which is the n torus, and in that case, this so-called higher index reduces to the family index. So this higher index is some unifying language of the previous three interesting examples. And why higher index is so we see that higher index lies in the K-theory of the reduced group system algebra. And conversely, one can ask this question: does every element of the K-theory of the reduced system algebra comes from the index of some gamma invariant operator? This is very interesting because this is related to a famous conjecture in non-commutative geometry, the so-called Baum-Connes conjecture. Namely, in 1982, Baum and Connes proposed an algorithm of computing the K-theory of the group system algebra by introducing something called topological K-theory of gamma. And this is something, some of the main object of today's talk. And going from that topological K-theory, one can formulate something called assembly map or something called higher index map into the K-theory of the system algebra. In 1994, this map is reformulated using analytic K-homology on the right and especially on the left-hand side. In any case, Baum and Connes conjectured that this map is an isomorphism. Of course, it is proved for some groups, but widely open for many discrete groups. If this conjecture is true, then one can say, well, every element comes from the K-theory of group system algebra. A reduced group system algebra is an higher index of some gamma invariant elliptic operator. So this built a nice connection between operator algebra and geometry. And this conjecture is important in non-commutative geometry just because it is in general very hard to compute the K-theory of the system algebra directly. And also it's important because if one has this isomorphism, then we have a lot of nice applications in geometry, topology, and representation theory. That is for the first part of my brief introduction of the context. And now I'm going to tell you something about this left-hand side of Baum-Connes assembly map, the so-called topological K group for gamma. So we now assume gamma to be a discrete group, and the overview of my talk today will contain like these three parts. We want to show that we want to show you how the topological K-theory is defined, and then we want to say that this topological K-theory for gamma admits a Chern character map, and that Chern character map is a result of Riemann-Roch theorems. And thirdly, I want to say that this whole construction will contain and assembles all index pairings for gamma proper actions. And lastly, I want to say that this topological K-theory is some object that represents the computable part of the K-theory of the reduced group system algebra. The computable means that you can compute that in terms of index theory. So in some sense, this left-hand side, this topological K-theory for gamma is something very local. It's computable thing. Okay, so now let us see how the topological K-theory for gamma is defined. But before that, let us recall what is the functorial map on K-theory. So for topological K-theory, so if we have two topological space between X and Y, and a map continuous function between two topological space, then one can have a natural functorial map on K-theory by pullback. Recall that topological K-theory of space is Grothendieck group of some complex vector bundles over that space. And given a continuous map, and given a vector bundle over Y, one can pull it back to a vector bundle over X, and that is a natural functorial map. And we also recall there's a wrong-way functorial map going from K-theory of X to K-theory of Y. That is the reversed way. And this is very important because in some special case, for example, if F is replaced by inclusion of a based space in its vector bundle, then this gives rise to the so-called, this push-forward map would give rise to the so-called Tom isomorphism on K-theory. And there's another interesting example when the map F maps into a point. So if Y is a point, then this push-forward map is simply the index map. So this push-forward map is very much related to index theory and Tom. Now we want to claim that for a discrete group and for a gamma equivariant map between two gamma proper co-compact manifolds M and N, there is also a wrong-way map or push-forward map going from equivariant K-theory of M to equivariant K-theory of N. And here, the equivariant K-theory is a shorthand notion of the operator algebra K-theory of the reduced C-star algebra of the transformation groupoid. But in case of M and gamma being compact, this is actually the equivariant K-theory. So we denote it like that. How does the push-forward map on K-theory defined? It involves formulation of deformation groupoid. If one has a gamma equivariant map F, then one can include M to M cross N using the diagonal map and the map F. And under this inclusion map, there is a normal bundle associated to this inclusion. The normal bundle is simply the tangent bundle of M, direct sum with the pullback of the tangent bundle of N. This is a vector bundle. This can be regarded as a vector bundle over M. And there is a deformation groupoid construction. Namely, one can construct a family of groupoid over the interval 0, 1, where over the point which is not 0, it is M cross N. It is some it's M cross N, and over the point 0, it will just be the normal bundle. So I don't have much time to say about the precise definition, but there is a very famous example, the so-called Conjecture tangent groupoid, which is a family of groupoid over interval 0, 1, and when the point is not 0, it is the pair groupoid M cross M, and when the point is 0, it is Tm. And you can glue this Tm to the rest part of the groupoid nicely, because this process, when T goes to 0, is you localize the you look at the diagonal of M cross M and localize to the diagonal localize to a neighborhood of the diagonal, and the neighborhood can be identified with the tangent bundle of M, and that is how the Conjecture tangent groupoid is constructed. With this deformation groupoid, let us denote the normal bundle regarding the inclusion by TF. And one can construct C-star algebras to that deformation groupoid and create two evaluation maps at 0 and at 1. And because the kernel of the evaluation map at 0 is contractible, so the evaluation map at 0 induces an isomorphism on K-theory. And because of all these preparations, one can finally define the push-forward map on K-theory by the following compositions of maps. So the first map is going from equivariant K-theory to equivariant K-theory of M to equivariant K-theory of the dual of this normal bundle, and they are actually isomorphic because of Thom isomorphism. And here we assume spin C structure of this T-F star to ensure this is an isomorphism, and it follows by a Fourier transform map, and then followed by the inverse of the evaluation at 0 map on the level of K-theory, and then followed by the evaluation map at 1, and then followed by some Morita equivalence map. So overall, it gives a map from K-theory of M to K-theory of N. So this of course looks complicated, but in the case of N being a point, this is a very familiar map. Actually, just Atiyah Singer's analytic index map. Let me try to explain that. So in that case, we're considering Connes tangent groupoid, where evaluation at 0 gives you Tm and evaluation at 1 gives you M cross M. But the C-star algebra of this pair groupoid is just compact operators, so the K-theory would just be the same as K-theory of a point, which is whose K0 is Z. And the previous arrows will be by Thom isomorphism. K-theory of M would be the isomorphic to K-theory of the cotangent bundle of M. Of course, we need to assume M to have spin C structure to be sure that it's an isomorphism. And then by a Fourier transform, and then by inverse of evaluation at 0 and followed by evaluation 1, we obtain a map going from K-theory of M or K-theory of cotangent bundle of M to Z. And that map can be proved to be the analytic index map by Atiyah and Singer. So this is a very famous map in the special case. In general, the push-forward map from M to N can be regarded as some sort of family index map. In any case, with these preparations, we can finally introduce what is the topological K-theory of discrete group gamma. So this group consists of cycles of the form M and X, where M is a proper co-compact spin C manifold, and X is an element in the equivariant K-theory of M. And we also need relations on these cycles, and the relations is precisely given by the push-forward map from M to N. In other words, the topological K-theory can be defined using the inductive limit of equivariant K-theory of M under these push-forward maps. Recall that in the definition, this manifold appeared, but the inductive limit will independent of manifold being chosen. Okay. So this is how we define the topological K-theory for gamma, and we want to say that recall that from K-theory to ordinary cohomology or homology, there are so-called Chern character map, and we want to say that we have an analogous construction on the cohomology level, namely given a nice map, gamma equivariant map from M to N, we not only can push forward on the K-theory level, we can also push forward it on the cohomology level. And with this construction, one can define we can define the ordinary cohomology theory for gamma using this inductive limit map. And furthermore, we can construct a Chern character map going from topological K-theory of gamma to this cohomology theory, ordinary cohomology theory of gamma. But in order to define that, one has to show compatibility of some diagrams, and that is what we want to say next. We want to show that we have a main theorem called Grothendieck-Riemann-Roch theorem. Okay, but to say that, we have to say what is the cohomology group used. We used the delocalized cohomology due to Tu and Xu. And this delocalized cohomology can be is essentially some so it is essentially decomposed into conjugate classes of gamma, and over each conjugate class, the component is just the cohomology of groupoid, and the groupoid is given by it's a transformation groupoid on the space of fixed point submanifold acted by the group of centralizers of a group element inside gamma. So it's very precise. And this delocalized cohomology have a lot of equivalence models called, say, Brandon cohomology, Chern-Albiford cohomology, and also cyclic cohomology of cross products. Up to rationally, they are all the same. But we choose to use delocalized cohomology by Tu and Xu because they are more attached to the formulation of groupoid. In any case, using this delocalized cohomology, we can formulate this Riemann-Roch formula. So the setting is, if we have a proper co-compact gamma manifold M and N, and a gamma equivariant map between them, and we require it's K-oriented, namely the this bundle is spin C. And in this case, we can push forward the K-theory map as we did in the topological K-theory of gamma, and we can also push forward on the level of cohomology, delocalized cohomology. And from K-theory to ordinary cohomology theory, we have the Chern character map. But one knows that from classical index theorem, this does not commute. So we fix the Chern character map by twisting the Chern character with the Todd class. And after twisting with the Todd class, we can make a commutative diagram. And we call that the Grothendieck-Riemann-Roch theorem in this setting. This is the main theorem. And we want to say that in case of gamma being trivial, then M and N, because the gamma action is co-compact, then M and N are just closed manifold. In this case, this really the Riemann-Roch theorem, because if one follows this commutative diagram first horizontally, then vertically, one gets the left-hand side. And if one follows vertically, then horizontally, one gets the right-hand side. And furthermore, if we assume N being a point, in this case, this Todd N would just nothing. So the left-hand side would just be F shriek of E, and the right-hand side, on the cohomology level, the push-forward map is just integration on the fiber M. So the right-hand side will give you the topological formula for the index of Dirac operator twisted by this vector bundle. So this is really implies the Atiyah-Singer's index theorem. And the idea of proof is also it's quite straightforward. Let us use the case of m being a point and gamma being trivial to show the idea. The idea of showing the commutative diagram is that one writes out the definition of the push-forward map on the level of K-theory in these left horizontal arrows, and also write down the push-forward map on the cohomology level in terms of this sequence of arrows on the right-hand side. And horizontally, one has the twisted Chern character map, and one just need to show on each diagrams here, on each box here, one need to show they commute, and one finally get a commutative diagram. So the commutativity of this diagram in particular shows the Riemann-Roch theorem for a closed manifold, which is essentially the proof of Atiyah-Singer. But in general, we can lift this diagram to a more complicated diagram and show the commutativity. So this is the idea of proof of our main theorem. So with our commutative diagram, we can say that if we take the inductive limit on the K-theory and also the inductive limit on the level of cohomology, with this commutative diagram, we can say that there is a well-defined map going from the topological K-theory for gamma to the cohomology for gamma. But specifying on each level, it will be equivariant K-theory for some manifold to delocalize cohomology for this manifold. So explicitly, this Chern character map has a nice formula in terms of the Chern character. Okay, this Chern character, the Chern character itself is actually not so new because by Baum-Connes and Hickson, one knows that this left-hand side of Baum-Connes map is actually the same as the analytic K-theory of the classifying space. And in that case, the Chern character is actually was constructed in several papers by Luke, Matty, and Voigt. But we want to emphasize that our construction really it's really very geometric. It takes into account of index theory. So it has a very nice index theory feature. But in the previous work, it was more algebraic. Okay, so this is the assembled Chern character. And what can we do with that? Well, we can try to obtain index formulas. We can try to obtain index formulas out of the topological K-theory. So by taking the so recall that there is an assembly map going from the topological K-theory of gamma to the K-theory of the C-star algebra. And analogously, one can have an assembly map on the level of cohomology, on the cohomology level. Namely, there is a map going from cohomology of gamma to cyclic homology of C gamma. And the cyclic homology of C gamma can be computed explicitly by the work of Bruglia, because here we assume gamma being discrete. So this HP C gamma is completely known, and one can obtain information of this group by pairing with the dual of C gamma, which is also well known. And by doing the pairing, one can calculate, one can have a cohomology formula calculating the pairing of the Chern character of the topological K-theory with an element coming from cyclic cohomology of C gamma. And the formula is given here on the right hand side. It is analogous to the Atiyah Singer, but it is more more general than that. Okay, and finally, so what we have been discussing. So finally, the summary is that we have been discussing making a Chern character of the topological K-theory of gamma, and then by pairing with a cyclic cocycle, one can obtain a number, and this number can be computed. So we have been working on the left-hand side of Baum-Connes map. But on the other hand, one can also first consider the assembly map, and then defining some cyclic cocycle of some nice dense subalgebra of C star gamma, pairing with that to obtain a formula. And we want to claim they are the same. But of course, this is future work. Up to now, we have been working on the left-hand side of Baum-Connes. And we want to say that our local index formula displayed on this page have some special case. So when we take the group to be the identity element, our local index formula will recover the higher index formula given by Kong and Moscovici, and they used that formula to prove the Novikov conjecture for hyperbolic groups. Of course, when they prove that theorem, they have to use the right-hand side of Baum-Connes to complete that. And in another direction, one can consider element coming from H0 of CT coming from a trace associated to a group element. And in that case, our local index formula recovers the L2 Lefschetz fixed point formula for all bifold done by Lin, Wang, and myself. I think that's all I want to say, but I want to add that all I talked about today is something local, because no matter the K-theory or the index formula we obtain from that, everything we obtained up to now are local. And that is basically because the index formula is computing, the setting of index formula is for proper co-compact action. But if one have some guess that the Baum-Connes conjecture is not true, then maybe one want to move to some non-local calculation. For example, when gamma is acting non-co-compactly on some manifold. And in that case, there are also a bunch of work. And for example, one can work on gamma acting on manifold with boundary. And in that case, the index formula will contain some non-local part, like gamma invariant will appear. And one actually hopes that in those cases, one may obtain some counterexample. But that is just some other thing I just want to mention so that it will be more compatible with the theme of the conference. So that's all I want to say. Thanks.
Thank you very much for interesting talk. Are there questions or comments? Maybe I add one remark. In the 80s, when Professor Antonevich pioneered the index theory and the elliptic theory for non-local operators, he considered the case of a finite group acting on a manifold, and he reduced the non-local operator for finite group to invariant operator, and as a corollary of Atiyah Singer, he obtained the contribution of what is in your language delocalized delocalized index formula, which takes into account fixed points. But
Okay.
on a closed manifold, so finite group, closed compact manifold. So maybe maybe for proper actions, maybe a similar approach might reduce. Maybe a similar approach might reduce non-local operators also to G-invariant operators, and your formulas might give
Yes,
as a
that's very
corollary
likely.
index for non-local things.
Yes, that's very likely, because proper action locally looks like finite. A proper action of a discrete group locally looks like finite group action. So very likely to be general.
Together with Boris Sternin, we were preoccupied with non-proper actions. So infinite group and compact manifold. And in that case,
in that case, a formula can also be obtained.
Yes, we obtained, for instance, for group Z. For group Z, there is a contribution only of G equal to neutral element of the group. Yes, and the formula includes Gorokhovsky approach to characteristic classes in his works. Gorokhovsky, Alexander Gorokhovsky, and we now try to write out contributions for non-trivial elements. And actually, Denis Perrault also wrote a good paper on that topic.
Yes.
So
okay. Those are very important references to look into. Thanks.
Is your paper already published, or?
This paper is already published.
With these three authors, yes?
Yeah.
Okay. Thank you very much.
Thank you. Professor
Schroer, did you have a question? Or?
Yeah, you said this is really computable.
Which is computable?
You made a point in the beginning that this group K-theory is hardly computable, but you seem to have.
I want to say the topological K group of gamma is computable, but the K theory of group system algebra, is it computable or not? It's not clear.
Okay. Thanks.
Okay, let's thank the speaker. Yes, thank you very much for interesting talk. And probably we